All right, so we're going to continue the part about different choice of priors. And I should say, I guess we were here last time talking about when you do standardization, you pretty much, for each observation, you take the mean from each observation, and then you divide that with the standard deviation of that variable, and you're going to get the standardized version. In R, you use the scale function. And the thing is, once you do standardization in shape, and the relationship between the two variables will change, they're just going to be shifted in terms of the scale. So you can see on the left-hand side and the right-hand side, there, the shape and the relationship doesn't change. But now we sort of put the log income standardized version as well as the log expenditure on the same scale to some degree. So you can see on the x-axis on the right is -4 to 2. The other one is -5 to 2.5. Okay, so there's definitely some skew in terms of both variables, because you get some extremely smaller values as well. And then we talked about once you do the standardization, the standardized version is talking about the value of it, is talking about the number of standard deviations away, either above or below the mean. So that would change our interpretation of the beta 0 and beta 1. So they are the intercept and the slope. So again, the intercept now becomes the expected standardized log expenditure, where xi star in this case is 0. So that's the observation which has the average log income. So similarly, when you have the slope, you are talking about the change in the expected standardized log expenditure when the standardized log income xi star or CUI increases by 1 unit. And equivalently, because now in this case it's 1 unit and it's standardized, so pretty much you are just changing that standardized log income by 1 standard deviation. All right, so the feature or the reason, I would say the cool feature of why we do standardization, because now the slope B1 equals to the correlation between xi star and yi star. So that's the standardized version. And we will know that, well, if you have a positive beta 1, you will have a positive correlation. If a negative beta 1, you have a negative correlation. The absolute value indicates the strength, and we know that correlation is between -1 to +1. Okay, so typically correlation is defined to be the relationship between two continuous random variables, and it should be between -1 and +1. Okay? So the smaller it is, or if the closer it is to -1, the stronger the negative correlation. The closer it is to +1, the higher the positive correlation. And if the value is close to 0, that just means that they don't have much correlation going on. So again, maybe before we talking about all of those correlation, anybody remembers the correlation definition in the first place? We covered that in many other contexts in the past. What do we mean by thinking about the correlation between two continuous random variables? Let's say we have x star and y star. Anybody? Vaguely remember? Mm-hmm.
Is it how much of the variance in y star is explained by x star?
Yeah, I guess, yeah. I think one way, let's see. Right. If we phrase it in that way, I guess it's more like we are doing a regression of y star given x star, and then think about how big the percentage. And that's typically probably what you have heard about the R square when you are doing a simple linear regression. So correlation, we typically use rho, and it's defined to be the covariance, the ratio of the covariance of x and y, so in this case star, and divided by the product of their variance, and the square root of that. Okay? So this is looking at, so each variable has its own variance. Okay, so that's fine. And but we also define covariance, thinking about how jointly they're varied from its mean, or their means at the same time. and then we define rho to be this way. So again, this should be a value between -1 to +1. The closer, so if you look at the like the form that we have, the closer it is to 0, the smaller the covariance, meaning that it wouldn't have much relationship going on or correlation going on. And the closer it is to -1 or +1, that is saying how strong the correlation is, but one goes to the negative side, the other one goes to the positive side. All right, so this is the thing that sometimes people might have strong opinion about what this rho should be. And then because after standardization, the slope beta1 just becomes the correlation itself. So we can directly now give prior to beta1. And that's why I think we want to do standardization in the first place, because now we can transfer our knowledge about the correlation to our belief about beta1. So for a demonstration, I think I probably like just pick some values that we can work with so I can demo with the R script. But you can choose your own as you like, especially if you have strong opinion about the correlation, you might choose a different prior, but we're all going to call this kind of prior subjective prior, because now you're inserting your belief in a subjective way. So the simplest case, again, we assume independence among all of the parameters. So that's why the joint prior of beta0, beta1, and sigma is the product of the 3 of them, which is in equation 23. So if we're going to focus first on the intercept beta0, so we know that beta0 now is talking about what the log expenditure should be for a CU with average log income, because not everything is standardized. And so in that case, well, so this is just one way to think about it. If you believe that the CU of an average log income will also have an average, like a log expenditure, like the outcome, like average transposed to the average, then you might just put a normal prior, say center as 0 for this beta0, because that's what the slope is about. And then, of course, sigma 0, which is the standard deviation for this prior distribution, is reflecting how confident you are about the guess of this beta0 equals to 0. Sometimes 0, 1. And as you can see that all of this can be changed by playing or tuning the standard deviation. So if you're pretty confident, then you can maybe put a small value for this. For not that confident, you can put a large value on this. But the reason why we put a 0 in the first place is because, well, if you do believe that CU of average X will also have an average Y. But if you have strong opinion otherwise, you can move that around. So that's what you can do about beta0. Beta1 is the one that we were talking about, because now it becomes the correlation. And if I have strong correlation, if I have strong belief about the correlation between the predictor, or the standardized, I should say, standardized predictor and the standardized response, then what I would do is I can put a normal prior for beta1, but then I can specify the particular values for U1 and S1 here. Say, I believe the correlation's best guess is 0.7, just say, I think that's what I believe in. Then I put 0.7 as the mean, and then this S1, again, is helping us to tune how confident we are or how sure we are about this guess. Okay? If you want to give it a large value, you're saying that it's less likely to be very much concentrated around 0.7. I want it to be varied a little bit more. Then you can increase this 0.15 or S1. But if you actually have very strong opinion about that, it should really just be 0.7. Then you can decrease that even further. So these are ways I think we've seen this many times now. So in this context, hopefully you know, first of all, what the intercept and the slope are representing. And second of all, if you want to give normal priors to them, what does the mean represent or what does the standard deviation represent? All right. Lastly, again, for the standard deviation or the precision is always really hard to figure out what it should be. So it's fine if you give it a weakly informative prior, and this is the one that we've been working with for a while now. So we're just going to get gamma 1, again for this 1 over sigma square for the demonstration. So this is the complete prior. I'm going to pause here for a little bit. You can see it's probably a good idea to write it out before you go to R or JAGS to code it up. Because once you can write out the model clearly, like including the sampling model as well as the prior choices, then putting it into JAGS will be pretty straightforward. Okay, so here I'm listing through equations 29 to 31, the 3 different priors that we're working with. Okay. Alrighty, so this is the model string, and I will pause here so you can digest what it is. It's going to be, yeah, I think overall it's similar to what we did before, but in this case, you will see that, well, I should say it's probably exactly the same as what we did before, but now for the next step, we know that we have to make sure that we standardize the X and Y before we pass the data into R, and also, yeah, for the mu0, g0, mu1, g1, those values, it will make sense. So I was still going to pause here for a little bit so you can check with the neighbor to make sure that you understand each line here, especially the sampling block where you have a loop, whereas the priors, like say you're working with inverse gamma 2 and then sigma itself. Oh, sorry, inverse sigma 2 and then sigma itself. I'm going to pause here for a minute. You can double check your understanding before we go on. Okay, any questions or comments before we move on? So the model overall makes sense. The model string actually, yeah, earlier I was saying that it's very similar. I think it's exactly the same as what we did before. But we're doing the weakly formative prior. But then of course the difference now becomes in here. So remember I used the scale function to transform the log total expenditure and log total income to the standardized version. So now I'm passing Y and X in that way. Okay. So this is where we're doing the subjective prior. So here N is still the length of Y. That's fine. The data, the list is fine. I think so. This few values here. So this are the gamma, right? The gamma 1, 1. So that's still the same. This is the I think the prior that we give beta 0, now we standardized it. And this is the one that we give for beta 1. So again, JAGS takes precision, so that's why you have this 44.4. I think I was using 0.15, right? For the standard deviation. So you will just use 1 divided by that square to get the precision to pass. And again, the init function is making your work reproducible, and this is exactly the same as before. And then lastly, we pass this over. So this, again, is exactly the same as before, pretty much. And I guess I just like, because everything is in the same file, as you go on Moodle, you will see the same R script file, the markdown file. So just to differentiate them, I just add the subjective. So later, when you're reproducing those results, you can have different ones you work with. So we're doing 1,000 adaptation, 5,000 burning, 5,000 sample. You can always start with 1, and then later for the thinning, if you see that the R correlation is high, you can increase that. And that's usually part of the MC diagnostics that you have to do. All right, so this is what we got for the summary. And I should also maybe just quickly show a little bit of the couple of MC diagnostics. Most importantly, we want to make sure that it's not sticky, as well as the autocorrelation is not high. So in that case, I think we are good. But before we move on, maybe think about the answers, or I would say think about what the parameters estimates are telling us. Especially, I guess, we focus on beta 0 and beta 1. So can we make any kind of interpretation and making sure that we know what is evaluating? Any issues to beta 1. Any issues to take away from the two summaries, beta 0 and beta 1? I mean, like, whoa.
You could use the median.
Beta 0 is about, on average, if you have an average standardized log income, what your standardized log expenditure should be. And then beta 1 is about the correlation, or like 1 unit increase in the standardized log income. So anything interesting that's worth mentioning before we move on?
So like the lower 95 quantile for beta 0 is negative, which is weird because I think it's like a variable that has to do with money, so, or with expenditure, right? So it kind of be weird to have spending. I don't know. I'm not like an economist, so but
Yeah, so, right, so it's actually easy to spot, I guess, in this case, that usually have a negative, like say lower bound, and its median is slightly negative as well. The thing is here, the beta 0 again, so if we write out the model, beta 0 is being applied on xi star, right? So the expected value of yi star. So the thing is, because now both of them are standardized, so when we
Oh,
standardize
okay,
them, right, the
It's
range
not- yeah,
actually,
it's
yeah,
different, is what you're-
exactly, yeah. So the range, so if you remember earlier, I think the range of xi star once we standardize is like negative 4 something to positive 2 on the graph that we saw earlier.
Mhm.
And then this one I think is I forgot exactly, but it's also something like 4.5 to positive 2.5, something like that. Yeah. So because of
Yeah, that
standardization,
makes sense.
yeah,
That's acceptable.
it loses meaning in its own way, but then beta 1 itself is easier to interpret because of the relationship between correlation and this. And not only easier to interpret it, but also easier to give prior on.
Mhm.
Yeah, so I would say like having a negative value.
That seems fine.
Yeah, it's fine. And I guess it's like the median and the mean. Yeah, both of them are very close to 0. That is to say, yeah, what does it mean? When we observe the beta 0 to be very similar, like very close to 0, what do we learn from that result in terms of the log, standardized log income and standardized log expenditure? Let me come back to the previous page when we wrote out the model and the interpretation.
They're all connected. So- Yeah.
So here, the intercept, so item 2 here.
So since it's close to 0, it's basically saying that a CU with average log income also has average log expenditure.
Once you standardize things. Okay? Yeah, so, and CU with standardized, average standardized log income will have on average standardized log expenditure to be 0. Okay? Yeah, so that's what beta 0 is about. And beta 1, let's see, we have roughly the numbers here. Yeah, beta 1, not only is a correlation, but also the unit increase and then the change in expected value, right? So I think we put it prior around 0.7, right? And then with 15% standard deviation, I think after we run the model, it's getting decreased a little bit, but still overall is greater than 0.5, something like that. So you can either talk about it in terms of the correlation, okay, or thinking about it as a change in expected value, standardized expected value. All right, sounds good? Okay, so that's the subjective prior, where you standardize the data so you can work on the correlation. And then you give your prior belief on the correlation through beta 1. The second and the last way to talk about a different prior choice is what we call a conditional means prior. And this is what the next lab, the last lab, 5, is going to be about as well. So we're going to cover the method, and then hopefully you have some time to work on the lab at the end of class today. So to summarize what we have done so far, weakly informative, you don't have much information about how you want to give prior for. And remember that for that kind of model, we're working on the original scale of the data, okay? And subjective for informative prior, we worked on the standardized version through the correlation coefficient. So the third approach, what we mean by the conditional means prior, so we're going to still work on the original data, meaning that's still the original scale. And what we're trying to do is to give the prior beliefs about the expected response value condition on specific values of the predicted value. I'll pause here a little bit. What this is saying, or I should maybe ask you, what do you think this is saying if I'm looking at my xi? Again, is the log income, and yi is the log expenditure. What do you think item 2 is talking about? So again, it's the expected response. So we're looking at the expected value of yi, which again is mu. Okay, so that's mathematically what we're talking about. And it's conditioning specific values with predictor variables. So what do you think? Like say in practice, what does this mean? And in what situation you would think that a prior in this way will make sense? I'll write one more line for you. So mu I we know is beta 0 plus beta 1 times xi. What do you mean by this? Like say, what do you mean by giving prior beliefs about the expected response value, which is mu I, conditioning on specific values of the predictor value? Sounds like we need to know, like say we have strong belief or certain belief about when xi taking a particular value, I sort of know what mu I should behave or how mu I should behave. Okay, so this is a situation, say, if you, from some other study or research that you got to know that if I know a CU having a particular log income value, and then I know like maybe it should, then the mean of the log expenditure should maybe roughly follow a particular distribution. If you have some kind of belief like that, then you can actually specify what we call a conditional means prior. So conditional is conditioning on the predictor value that you have, okay? And then it's through the means, mostly because now we're trying to express our prior belief in terms of mean. Right? So again, xi is always given, right? You know what it is, it's in the data. And we also know Bayesian methods assume that beta 0 and beta 1, they're random. It's hard for us to give prior to beta 0 and beta 1 directly. So instead of giving them directly, we might come up with ideas that if I know a certain CU has xi, say 1, then I'm guessing that the expected value of the response may be a particular normal distribution. I have the standard deviation for that. Then I can specify my prior in this way. Okay. So before I cover like the details of how to do it, I just want you to get the mathematical sense here, because this is given. So this is fixed. Xi is fixed. This too should be random. And what we're trying to do now is also giving a random distribution for this mu I given a fixed xi value. Okay? So if I do that, I'm sort of indirectly giving prior distribution for beta 0 and beta 1. Right? So if that is the case, and I do want to have estimation about beta 0 and beta 1, based on the setup here, how many different means I need to have, or how many different xi values I should pick before I can solve this. This is a math problem, in a sense that these are the two unknown that I'm trying to solve, okay? And I don't know what they are. It's hard for me to give priors to them, so I don't know. But I do know their relationship between xi and mu I. Now what I'm saying is we're going to give random distribution for a particular mu I given the xi value. So my question for you is how many different xi's I should try to give prior on so I can have my results for beta 0 and beta 1.
We just need 2.
You need 2, right? Because if you have mu I, let's say 1, which is beta 0 plus beta 1, xi 1, and then mu I2 equals to beta 0 also plus beta 1 xi2. Yeah, so with this two, like Juanina and many other, I guess, got this as well, that what we need to do is, these two are the unknown, right? We know these two are fixed, and we are able to give prior distribution for them because I have 2 unknown, so I should have 2 equations to solve, okay? So that's why, so soon we're gonna see the mechanics of how to make this work, but I do want to mention that for conditional means prior, if you're working with 2 coefficients, you need 2. prior choices for 2 different xi. But if you're working with later next week or after Thanksgiving, you're going to cover the multiple linear regression where you have multiple predictors, meaning that you're going to have multiple coefficients that you're trying to estimate. If you want to do this through a conditional means prior, how many how many coefficients you have, the number of that determines how many means you have to give or how many priors you have to specify. Okay. So I think that's good to know just to get it set up. So what we're going to do, assume independence, and then focus on this linear relationship that we just talked about. So right now we already discovered that we need to choose 2 particular xi values. So we are able to formulate the prior opinion about beta 0 and beta 1 through the mean. So let's say this is hypothetical. If I think that for the first particular predictor value xi, I can construct a normal prior for mu I through this prior. Okay? And specifically, let's say xi is 10, which is the log income to be 10 for a particular CU. And then say I believe the mean mu1 should follow normal 10 and 2. Let's just say this is how, like, say I have some like opinion about this. It's really hard, I think, in this context to think about them because everything is on the log scale and all that. Any other application, I hope it's easier to do. So let's say we have this first prior set up for mu1. And similarly, if I have another CU with log income to be 15, and I believe the mean should be a normal 11.2. So these are, again, sort of hypothetical just to show you how the conditional means prior can work. And I came up with them just like based on my guessing. And again, if you do not have very strong prior relief and then say give larger standard deviation for them, you will let more of the data to drive the inference regardless. Okay? So let's keep in mind. And again, we show that because you have 2 unknowns, so you need 2 set of x and mu to figure out how you can solve the other ones. Okay, so keep those in mind. And in the lab, you will see how to do things carefully. So then lastly, equations 38 and 39 is sort of like work out the math and then try to express my beta 1 and beta 0 in terms of mu1, mu2, and then x1, x2. Okay, so this is rearranging. So earlier we were saying that we have 2 unknowns, so we need 2 equations. So we have mu1 equals to mu0 plus, beta 1 plus beta 0, beta 0 plus beta 1 times xi, and mu2 to be beta 0 plus beta 1 x2. Okay, so now I try to solve beta 0 and beta 1. So if I rearrange the terms, I will get my equations 30 and 39. Okay, so before we get to the R script part, just want all of us to think through what we're doing here. You can express your beta 0 and beta 1 in this way through the mu1, mu2, x1, and x2, right? So what is x1 and x2? Earlier, we picked some numbers for them, right? I think one is 10, the other one is 15, something like that. So this is always going to be 5, right? And this is always going to be 5, and this is always going to be 10. Okay, they're fixed, yeah. What I want to show you now is what is changing and what is fixed. So x1 and x2, they're fixed, so their difference is fixed. And for mu1 and mu2, if you remember, mu1 we give a normal prior, a2. mu2 we give another normal prior, what is it, 12.2, something like that. Then you will see that, well, when I'm trying to make inference about it, from the Bayesian methods, we know that we're going to get a bunch of draws about mu1 and mu2 because they are random, right? Let's say we have 5,000 draws of them. So what that translates into, if you imagine equations 38 and 39 now in action, that if I have 5,000 draws of my mu1 from my MCMC, right? I have another 5,000 draws from of mu2 for my MCMC. What that translates into is by applying 38 and 39, I'm gonna have 5,000 draws for beta 1 and 5,000 draws for beta 2 for beta 0, right? So yeah, so this is how you can think of, well, even though we know that we started with beta 0 and beta 1 to be random, but it's so hard to give prior on them directly, we can think about indirect ways to do that. And then in this case, we are giving prior on the mean given particular xi value. So the mean is mu I. And we always know their linear relationship. This is always fixed because that's the basic of the linear regression that we're working on. And what that translates into, as we just talked about, after my MC inference, I can have a bunch of mu1 and mu2 draws, let's say 5,000 of them, right? And x1, x2, they're always fixed. So you look at equations 38 and 39, what that means is with the 5,000 draws of mu1 and 5,000 draws of mu2, which is in here and also here, I will get 5,000 draws of beta 0 and 5,000 draws of beta 1. So in the end, I will still get posterior estimate of the correlation, of the regression coefficients, even though I started off by giving prior on the means of the mu1 and mu2. Okay, yeah. So just imagine ahead. Soon you will see that in JAGS, what that means is, well, I do give prior to mu1 and mu2 directly, like normal, what I would write out, right, in the prior block. But I should have those functions to return my beta 0 and beta 1, because those are my interests. Remember, in the normal model that we've been doing, we always have to give the precision for the d-norm function in JAGS, right? So we've been doing like inverse sigma 2 or inverse tau 2, something like that. But at the end of the day, we're interested in what? In sigma or in tau itself. So we always write one extra line at the bottom of our JAGS code in the prior block that we want to return sigma using the power function, square root, all that. So this is also, so you will see soon that to reflect the fact that we want to get draws of beta 1 and beta 0, we're going to actually have to express 38 and 39 in our JAGS code. Because at the end of the day, we want to save draws about them, not the mu1 and mu2. Okay. All right, so this is a long preview, I guess. I should just show you the script so you will see it. Anyway, so again, this is the one that we're using. So this is the script that we have. So I'm going to pause here based on what we discussed just now. If you go through the steps, especially like the priors block right now, because now this is looking different from before, because we're giving prior on mu and then try to get the beta 0 and beta 1 from them. Okay, I'm going to pause here for a little bit and we can look at the results together.
Any comments, questions about the script?
Well, I just realized this is the lab slide, so I think this is actually the gateway to the lab 5. But before we start doing that, any general questions about the way that we set it up with priors? I mean, now we can start working on lab 5, because then you will get into the detail of how to, like, of course, later on, how you're going to pass the data into it, how you can summarize things. So you can start that now. So let me